A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I am your host Yusuf, and for this episode of the podcast I'm very excited to welcome Aidan Wimshurst to my show. Aidan is a chartered mechanical engineer based in the United Kingdom, specialising in computational fluid dynamics, short CFD, and heat transfer. Aidan addresses industrial fluid dynamics and heat transfer problems across a range of sectors and routinely develops solutions to complex modelling problems including conjugate heat transfer, solid particle transport, and rotor aerodynamics. In his spare time, Aidan teaches computational fluid dynamics online through his popular YouTube channel Fluid Mechanics 101. His aim is to encourage and inspire engineers and provide them with the tools they need to solve the world's most challenging fluid dynamics problems. In this very exciting podcast, we talked about computational fluid dynamics, OpenFOAM and how to get started with it, bottlenecks in CFD, most common problems in CFD, how to approach CFD problems in general, and much more. For updates on upcoming podcasts, projects and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter engineeredmind.sh where I share exclusive content, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Aidan Wimshurst. Hey Aidan, welcome to the show. It's a pleasure to have you here.
Pleasure to be here, Joseph.
Awesome, nice to meet you and finally have you on the show because so many people requested, hey, get Aidan on the show, get Aidan on the show. So finally we have you on the show and we want to talk about plenty of stuff actually, in particular about CFD. But before we jump into the nitty gritty and CFD and all these kind of things, can you give us like a 1 or 2 minute bio? Who is Aidan and what do you actually do?
Yeah, of course. I don't think I've actually given my bio out really anywhere before, so this will probably be quite interesting for people listening to finally hear where did I come from before I appeared on the internet. So maybe if I start things back when I was 17 or 18, going through secondary school as we call it in the UK, or high school as they call it in the US. I was studying science and maths subjects like most people do. And I didn't really know what I wanted to study at university or college. I didn't really know what I wanted to do. And so I looked at all the options, and there are lots of interesting things you can do in science. You can go into to medicine, to engineering, to physics, biology. And I was drawn a bit towards physics at first. I thought physics sounded interesting. People were doing lots of things with particles and space and galaxies. And I thought, that sounded quite interesting. But I thought about it for a while and I discovered engineering. It was the first time I discovered engineering when I was looking through the brochure to find what courses can you study at college and university. Because this was back in the days before really social media was around and was a big thing. This was kind of before YouTube and before Facebook. So it wasn't really a time where you could go on the internet and look for examples of what people did. Mm-hmm. And I looked and I found engineering and I thought, this sounds interesting. It sounds like physics and science, but it's a bit more applied to real world things. I mean, I always found space and galaxies and neutrons and things very, very interesting, but it was quite hard to grasp what these things actually are because they're quite far away from home and you can't really sort of visualize and picture what these things are. But the draw of engineering seemed to be, you can actually work on things that you see in your everyday life. You can work on the cars, the boats, the planes, the power stations. And I thought that sounded quite interesting. So I signed up and went away to the University of Southampton in the UK, which is it's a really good university. It's on the south coast of the UK. So they have lots of ports and ships and boats going through Southampton. It's quite a famous maritime city. And in Southampton, their traditional engineering course, like many engineering courses are around the world, you go into engineering and you start by learning a broad spectrum of everything in engineering. You learn some solid mechanics, you learn some electricity and magnetism, some fluid mechanics, some design, mathematics. And again, I was just sort of going along and seeing what was happening, but I didn't really know what I wanted to do. And I imagine this is the case for many young people going to science-based degrees and topics. You turn up at university and you think, I think this is what I want to do, but I'm not really sure. And you start learning, and then you actually learn about the field in a bit more detail, and you start to realize maybe I don't really like the solid mechanics and structures and things. Actually, I find it quite boring, or the thermodynamics is just too hard, it's too complicated, as I hear many people say. So that's the situation that I was in. I just turn up as a fresh student at a university, trying to decide what it was I wanted to do. And in my second year of university, so this is probably back in 2012, 2011, so early days of social media, I had a really fantastic lecturer for fluid mechanics. This was probably one of the best lecturers I'd ever had. And my lecturer at the time, he was an aerospace engineer, so he talked about airplanes and wings. And one of the things he did, which was so fantastic, was he started from very first principles, talking about the Navier-Stokes equations and fluid mechanics, and actually took the time to explain what the pieces meant, what was going on. This part of the equation represents this, and you see this in this sort of phenomenon. This part of the equation over here is associated with turbulence. This is actually where turbulence arises and is generated from. And for me, I found his approach was really, really captivating for me, because for the first time, rather than turning up at school or university and being given, here are a set of topics which you have to remember. You have to remember these topics. Here are some equations that you need to remember. Here's an exam paper, and you need to solve the problems and get the marks as best you can. With this lecturer, he actually took the time to explain how everything worked. And for the first time, I could see a sort of a complete picture starting to form of actually, in the topic of fluid mechanics, this is where all of the parts fit together. And this is what pressure is, and density, velocity, how these things fit together. And when you understand it, you could actually start to build up an understanding of where all the pieces in the universe started to fit together. And for some reason, that really clicked with me. And I thought, this is actually something that I enjoy, and I can actually work things out and understand things from first principles. And this is what I try and bring to my teaching, at least on YouTube, is that I really try and bring it from that kind of an approach that I had when I was in my second year of university. I try and bring things out from the understanding from first principles, building them up with simple pictures and ideas, and then bringing them together so that eventually you know which is the button to press in my CFD code when I do it. But this is quite a long rambling story. Hopefully you're finding it interesting. But at this point, I hadn't done any CFD at all. I'd done no CFD at all. It was all learning at university. What is fluid mechanics? How can you calculate the forces on a dam? There's lots of things which many people have to do in their university courses. And I finished my undergraduate. And at that point, once again, I also didn't really know what I wanted to do. You know, presented with a very exciting and deep world in front of you with many different job opportunities and career paths you could follow, was that with a science background, particularly nowadays as well. I think it's the range of choices you have are even more varied. You've got your classical subjects, but then you have lots of interesting new fields. Certainly fields in sort of AI and things like that seem to be very popular nowadays. There are all sorts of things which you could go into. And I didn't really know what I wanted to do. I had a little look around, and in the end, I found a PhD program that was advertised looking at tidal energy and tidal stream turbines. And I looked at it and thought, oh, this is fairly interesting to me. It obviously uses a lot of fluid mechanics. Maybe I could try and give that a go and see if I like it. And I then turned up at Oxford University in the UK to look at tidal energy, tidal stream energy, and went into day one once again as a very open book. Didn't really know what was going to happen, didn't really know what I was going to do. And over the first few months, that was where I first found CFD and had my first go at CFD. I hadn't really done any CFD at all over my undergrad. I'd just been doing fluid mechanics, and I arrived at CFD for the first time. And I always find it interesting how people first come across CFD. It's quite a niche field that you have to get to quite a high level in science before you find it or find some use for it. And the CFD code that I was presented with was OpenFOAM. I turned up and, oh, it looks like for your project, you're going to have to use some CFD. And I think this is something that tends to happen to a lot of engineers as well. You're studying a real system, or you're trying to look at some problem. And then over the course of looking at that problem, it becomes revealed you now need to use a technique, which is called Computational Fluid Dynamics. Give it a go. So you end up with a CFD code, whatever you get access to, whether you've got access to Fluent, Star CCM, OpenFOAM, or maybe a university code. You're given the CFD and you think, I now need to work out how this works. What do the buttons mean? I then need to get a solution, and I need to somehow use that to support my engineering work that I'm doing. And so I was first presented with OpenFOAM. I think I started on OpenFOAM 2.3 was the OpenFOAM version that I was using when I first started. I think they're now on about OpenFOAM 7. And I somehow had to work out what is CFD, how does this relate to fluid mechanics, what's a boundary condition, what's a mesh, all of these things I had to learn. And so that's one of the other things that I do try and bring to my teaching as well, is that I have, over the past few years at least, built up my understanding and my experience from the ground up, and it's still very close to home. I remember very much what it was like the first time I picked up the CFD code. And I hope that's one of the things that many of the listeners of your channel and my channel will find useful, is that I still have in my sights what it was like the first time I opened up a CFD code. And I know that after a few years, often details can get lost to you. It's difficult to remember what you were doing 5 years ago or 10 years ago. But I do hope that with perhaps 5 or 6 years of experience under my belt, I'm still close enough to home that I can remember the struggles of first using OpenFOAM. And OpenFOAM's not an easy one. I'm sure many people who use it will know. So hopefully that's a little background history of where I came from. Fairly typical engineering career up until this point.
Great. So there was a lot of things that you mentioned. We want to touch on some of those points. Let's maybe start with OpenFOAM. If you look back, and now let's say you have to start with OpenFOAM again, because a lot of students that I know, and also I had to start with OpenFOAM. What would you do differently when you use a CFD code? Would it just be jumping straight to the documentation, or what would you do in order to learn OpenFOAM from scratch?
Yeah, definitely the thing that I would do, and I've had a few emails from people asking me how to do this. They say, oh, Aidan, I need to use my professor has told me I need to use OpenFOAM. I need to get a solution to this problem. What should I do? And I have something I would do, and then something I wouldn't do as well. The first thing I would do is absolutely go through the tutorials that OpenFOAM provides. I think they start with a lid-driven cavity flow, I think is the first one, where it's just a box and you have the top of the box is moving and it just sets up a nice recirculating flow in the cavity. So absolutely my advice would be go on the OpenFOAM website, find the tutorials and just start with the first one and just go through it line by line to work out what on earth's going on here. Can I use a terminal? Have I even got OpenFOAM installed? How can I get some results? How can I look at them? What is this folder structure that's going on? There's a zero folder, a constant folder, a system folder. Isn't this all just saved in a file? That's what I normally have. So I'd absolutely go through all of the tutorials. Go through the first one, the second one, and then go through a couple until you've got an idea of actually how this is working. How's the file structure working? Where do I need to put things? What's being written out? And the thing I would recommend not doing is, at that point, you can probably get to a situation where you think, I think I've understood enough now that maybe I could give it a go at something that's similar to my problem, but maybe not my exact problem. And what I did when I started with OpenFOAM is I started using the block mesh tool to make my mesh. I don't know if you have any experience with this. OpenFOAM has its own meshing tool that you can run to make a block structured mesh, where you actually label where the corners of the block are and the number of cells across the block and how will the blocks map together to construct the full mesh. And this took me, I remember spending weeks and weeks of time on pieces of paper just drawing out the block structure, where the corners were, how all the blocks linked together, putting it in a file and trying to create the mesh, and then it would error and the cells would be skewed over. And it took me weeks and weeks. And I then found out and realized that the university actually had access to mesh generating software that I could have just used. And that's one thing OpenFOAM does have, is it's pretty good at being able to read in meshes from other mesh generators and sources. And that would have saved me, as an easy time saving, that would have saved me months of time just making a mesh in a proper program, just bringing it in. So at that point, you've done your tutorials, you've maybe made a mesh using something, whatever you have available, whatever's sensible to you. And I think the best piece of advice I can give with something like OpenFOAM particularly is to try and build up your case in stages, build up the complexity of what you're doing bit by bit, really, really take it slowly. And the way you would probably do that is find a tutorial that's pretty similar to what you're trying to do. Maybe it's the cavity flow, maybe it's an aerofoil, maybe it's something heated, a heated channel or something. And then just change things bit by bit. And it will take you a little while to get used to, but then slowly develop your case. And I found, for me at least, with OpenFOAM, it's a lot easier to start with a very simple geometry with hardly any cells in your mesh. So you may have a really complex case, you may have something with millions of cells, but just try and make your case maybe with 10,000 cells, just with the boundaries, everything labeled, and just so you can get the setup and everything right in OpenFOAM, because everything does get a lot heavier when you have a bigger mesh. So just try something really simple first. Just flow in a box tends to work quite well, I think, for setting up the case, and then add the complexity bit by bit.
Yeah, interesting. And thanks, Aidan, for triggering my PTSD when it comes to block mesh. That's great. You talked a little bit about the process from CFD. So let's say you would have to give someone advice on how to approach the CFD case. Of course, we all know these steps like pre-processing, processing, and post-processing. How would you personally approach a case? Let's say you have a brand new case, you don't know how to do it. You laid out how you would do it, like step by step, increasing the complexity of the case. But how would you go from beginning to the end? Maybe to give new users in OpenFOAM who listen to the podcast some kind of an insight of how you would do it.
Yeah. Something which I've actually changed my approach over the last few years from experience of running quite a lot of CFD cases. And actually, there's an additional step which I think a lot of people don't tell you to do when you're doing your CFD, which I've now found has been really helpful. And that is trying to solve as much of the problem by hand as you can, actually trying to estimate for yourself what should the answer be. So for example, let's say you were doing the very simple case of flow over an aerofoil, for example. You have a large domain and you've got a small aerofoil in the middle, and you want to calculate what the lift and drag on the aerofoil are. That's a fairly standard problem. And the first thing I would do now, if I were to solve the problem, is just get out a piece of paper or Microsoft Excel and try and work out, what do I think the solution should be before I even start? Can I guess what I think what the solution is going to be? And you can often get very far by looking at research papers or other people's theses online, actually finding, have other people done this before? What did they get? You might be able to look it up, find a thesis or a paper, and you might find, for this particular aerofoil, I'm expecting an angle of attack of 8 degrees, the lift coefficient to be 1.2, for example. I think the lift coefficient is going to be 1.2. I think the drag coefficient is going to be this much. This is the solver I'm using. I'm expecting it to converge in this many iterations. I expect the forces to look something like this, and to actually try and work out what is as much of the solution going to look like as possible, because that often helps you then in the setup when you then set it up and you think, I know the forces are going to be about this. I know the temperatures are going to be about this. So definitely for when you set up your monitors, for example, and checking that your case is running correctly. Have I got the flow going the wrong way? That's quite a typical one. Which way should the flow go? Should my mass flow be positive or negative? That would definitely be the first thing that I do. And this tends to help for very simple cases like aerofoils. There's not a lot of information you can pull together. But when you get to more complicated cases, maybe you have things with temperature, with heated surfaces, maybe with multi-phase flows, for example. You may be able to work out things like, what do I think the heat flux is going to be coming off my object? Can I model it? Can I assume it's a cylinder or a cube, and then look up in a textbook, the heat transfer coefficient will be about 10, for example. And just getting an example and try and work out as much of the case as you can by hand first before solving it is probably the best thing I would recommend.
Mm-hmm. And when it comes to the other steps, like in the CFD process, for example, post-processing, what would you say are the biggest bottlenecks in this whole CFD process?
Oh, yeah. Yeah, definitely. So I'll do pre-processing first. Mm-hmm. I'll do pre-processing first. So you've done your hand calculations and you've tried to work out as much as you can of what you think the solution is going to be. And the next thing will be building your geometry and building your mesh. That's usually the case with your pre-processing. One thing which is, I was talking to a colleague the other day about this actually, when you're generating a mesh for CFD, when you're quite new, you may think that out of the time I spent building my mesh in my program, I may think that, actually 90% of the time will be spent building the mesh, and then perhaps 10% I'll spend fixing it and improving it, trying to reduce the skewness and the non-orthogonality and the aspect ratio, and just fixing it and reducing some of the bad areas and manipulating things. That's often what people think when they come to meshing. But in practice, what happens is you probably spend about 40 to 50% of the time just making that first mesh. And then all of the time in meshing is often spent just fixing those few little problems that you have. And it's often things, your inflation layers are compressing, or the cells are being skewed by a bit of surface. Those small problems can take hours and hours and often days to fix. So when you're planning your time and you're thinking about your meshing, I would fully anticipate that if, let's say, it took you a day to produce your first mesh, definitely expect at least that length of time where you'll just be spent making tiny adjustments to it, trying to move cells around and just adjust inflation layers and things ever so slightly to improve that mesh. That's definitely something that can help you for your planning. And in terms of the overall process of the project as well, because the meshing is such a bottleneck and it's so difficult, particularly if it's a big project. Another useful thing which you can think of when you're doing these problems is to think of, rather than just the CFD code itself being an iterative solver. So a CFD solver makes a guess at the solution and then improves it until it converges to some tolerance. You can also think of your entire investigation as an iterative process as well. That really helps. You'd fully expect that you'll make a mesh, set it up in your code, run all the way through, get to the end, get your answer, and then find my mesh is perhaps wrong, or I need to change my boundary conditions and I need to go all the way back to the start of that process. And it can often take you 2 or sometimes 3 loops through that process, particularly if you're doing something in academia to get that solution that you're really interested in. So you can, with your pre-processing step, with that in mind, you can also just go in with a rubbish mesh, go in with a mesh that's terrible. That's something I often do. I'll get my geometry and just throw in a rubbish mesh, maybe only a few inflation layers or maybe none at all, maybe only a couple of 100,000 cells. Just go in with something rubbish and just run through the entire CFD process so you can get to the end and so you can iron out all the creases and work out what's going on. So that's another thing you can do, rubbish mesh for your first go. And the next thing would be definitely thinking about the scripts that you're going to set up to do things as well. And the reason you might want to think about how you script your CFD in MATLAB or Python, they tend to be quite popular, is if you think to yourself, my first go at this CFD problem, I'm probably going to get the answer wrong. I might be off by 20%. I'm probably going to have to do it again because I've missed something. Then it can be quite useful to try and automate things as you go along. And that's particularly the case in OpenFOAM, where you have lots of files all over the place. It can be quite useful to, for example, make your own script that will go into your monitors and just pull out your force data and do your integration for you and make a plot, for example, of your convergence. That can be something that's quite useful to do on your first go. So you've made your coarse mesh, something that's really rubbish. You've jumped straight into your CFD code, run it, it's converged, and you've spent a bit of time writing a script to pull out the things you want to do your post-processing. And the reason why that's then good is you can then just go back to the first stage in your process and do it all over again, but you've done all of the hard work up front. The only thing you're changing at that point is perhaps the mesh or the boundary conditions. that's how you can do that with monitoring. And one thing I've noticed as well with a lot of people who are new to CFD, including myself when I first started, is you may find that when you open up your post-processor, if you're in ParaView or Field View or TechPlot, one of these programs, making things like contour plots and line plots can take quite a long time. And there's lots of clicking. Maybe I'm going to adjust the contour a bit, and maybe I'm going to move it around, and actually the slice I want is perhaps over here. That can take quite a while to do, particularly if you're going to make multiple contour plots. And most post-processors actually have the capability to script that action itself in quite a few of them. I think use Python seems to be fairly popular, or other languages. There's often an interface where you can tell the post-processor, take my contour plot here, these are the levels I want, this is the view I want it to be. And that's another little script which you can start working on as soon as you start doing your project, so that then when you go back through and you have to change your mesh again, or you find that your flow rate or your conditions were wrong and you have to rerun, that your scripts are already set up. So you load up the post processor and click run, and it will create all of your contour plots for you. That kind of automation is very useful and can save you a lot of time, definitely in the long run.
Mm-hmm. You also talked about the convergence aspect. Could you quickly define what does the convergence even mean, or what does the word convergence mean? Because there's so many aspects to convergence. And what does it mean in terms of CFD?
Yeah. So convergence is something that I think confuses quite a few beginners when they first start with CFD. The reason it can confuse beginners quite a lot is you often load up your CFD code, be it Fluid or CFX or Star, and you run your first program, and you usually see a plot of residuals from the transport equations. And they have a very typical shape where they all start up about 1, lots of colored lines, and then they drop down a bit, and then they start wiggling around and stay horizontal. And as a beginner or a first-time user of CFD, often it's assumed that when the lines stop going down and the residuals stop going down and it starts just moving across and wiggling around, that I've reached convergence. That's often what a lot of people think. And what often the next question is, well, how far down do the lines need to go? What happens if my line goes down to 1e minus 2 and then wiggles across? Is that converged? It's not moving anymore, but has it gone down low enough? And there's definitely those questions come up a lot. There's not an easy answer to them, and it's quite a frequent stumbling point for beginners. So what is often then the advice given to many people is that you shouldn't just use residuals to judge convergence of your CFD case. And as well, what does convergence mean? Is it just that the white lines are wiggling? How else do I judge that? Well, firstly, we're probably used to the idea that because we're solving some equations in an iterative manner, every time we solve the equations, hopefully our solution will continue to improve as we make continued guesses. And often the criteria that people use for convergence is they say, well, perhaps the solution that I'm getting from my next guess or iteration is staying the same. I'm not improving anymore. The residual, as they often call it, the part that's left over from your solution, that's not getting any smaller. That's often what people mean when they say convergence. And there's definitely some differences in terms of what an engineer would call convergence as to what a mathematician would call convergence, or a computer scientist. If you were a computer scientist or a mathematician, you'd want to continue running that iterative solver until the residual, the bits that's left, gets down to something that's called machine tolerance, where the number is so small that it's indistinguishable from the resolution of the numbers that the computer stores in its memory. That's what a computer scientist or a mathematician would usually go with for convergence. But for an engineer, the problems we solve are often non-linear, they're very complicated, and we often can't bring that residual all the way down to a machine tolerance. And so what people tend to do is rather than looking at a residual, which doesn't really tell us anything, the trick is to look at the quantity that you're interested in. What quantity are you going to use as an output from your solution? Am I looking at the lift coefficient for an aerofoil, for example, or am I looking at the torque from my rotor or my propeller? That's often the thing that you're interested in. And so a better way to judge convergence is to look at the residual and to also look at the quantity that you're interested in, and look at what happens to the lift coefficient on the aerofoil as I continue to simulate my CFD code. If my lift coefficient gets to a value of 1.278, for example, and then continues to move around a little bit around that, in my subsequent work, if I'm going to say the lift coefficient is 1.2 or 1.3, then that simulation is suitably converged for your application. So that's really the thing to pay attention to, is how is the real quantity that you're interested in changing as you continue to run. If I run another 2,000 iterations, does the lift coefficient stay at 1.273, or does it continue to go up? If the quantity is still changing, then your solution's not converged. And this is why for beginners, what's recommended is that as well as you looking at residuals, you should also put a range of monitors on other quantities in your flow field. So the thing that you're actually interested in, you should probably watch how that changes as your solution converges. And you can do this with point monitors, with integrated monitors over surfaces of forces and things. And most CFD codes have the capability to do this. So definitely you want to look at everything. And you may find, with a bit of experience, that you'll find that some things converge faster than others. And this is what you'll start to find as you do more and more CFD. You'll find things like, for example, if you're doing the aerofoil, you'll find that the lift coefficient actually usually converges relatively quickly to the value that you're interested in. You may find that within 500 iterations, you've got your lift coefficient at 1.273. But if you were interested in the flow field, maybe if your aerofoil has a separated flow and there are vortices coming, trailing vortices coming off the back, if you were to monitor the flow field, you find that the flow field actually takes a lot longer, and it may take several thousand iterations to get to the point where it's suitably converged. So really, really important to look at the thing that you're interested in, not just the residuals.
Excellent explanation. Thank you so much, Aidan. When it comes to all the methods that we have to simulate CFD, whether it's FDM, so finite difference method, finite volume method, FEM even, what would you say? Let's say you're in academia, you take a course. Would you start, or would you advise students to start with a finite difference method, just to get a grasp of CFD, how it works, how you derive, what does this residual mean, and what does a Taylor series mean, for example? And then if you move towards real-life applications, use more FVM methods?
Yeah, I would definitely agree. I think the best place to start is definitely with a finite difference method. Finite difference methods are the easiest to understand, and they're closest to the differential equations that you'll study in mathematics courses. So definitely start with the finite difference methods first, and you can get very far in understanding just by learning those. But then I would recommend moving on to looking at finite volume methods afterwards. The reason for that is the majority of CFD codes that use in industry and in academia all use the finite volume method. And the reason they do that is principally because the geometries that we look at in CFD are often very complicated, curved surfaces and things like that. And so it's worth moving on to the finite volume method as soon as you can, because what is often the case for most CFD engineers is you start solving a problem and you get stuck, and you want to know, how do I do this particular bit of functionality in my code? What does this error or this message mean? What is this discretization scheme for convection that I'm seeing? And in order to be able to understand that in the user manual and on the forums, you need to understand the finite volume method. So I think finite difference method for first learning, but then moving on to finite volume method straight after. With finite element methods, they are used by some codes. So really it would depend on what you're doing in particular. So if you were in an academic environment or an institution that had their own finite element code that they used for their problems, then it would be worth learning that. But if you were in an environment where you're using a finite volume method, definitely learn that. And most of the commercial CFD codes do use finite volume method. That's why I tend to prefer that one to the finite element method.
Great. Also, Aidan, you have some courses that you put on Udemy, and you also have your own website about courses. So you can quickly put in an ad now for like all of the courses that you have. And what do these courses cover, and who should take these courses? Maybe just
of course. So my courses attempt to exactly bridge the gap between the finite difference method and the finite volume method. So when you're in your university courses, chances are you may, over the course of your university courses, be asked to solve simple problems like heat conduction in a rod or a bar, or heat conduction in a plate, for example, using the finite difference method. And you can solve that, and that's fairly simple to do, and it's a good learning exercise. What my courses then do is take the first course at least takes that same simple problem, so heat conduction in a bar and heat conduction in a plate, and solves that with the finite volume method. So again, it's the same problem. It's about the simplest problem you could solve with a finite volume method. And so it's very useful to just get to grips with what are the key aspects of the finite volume method. How does it work? So you can really get that first stage in understanding for the finite volume method. That's in course 1. And what I do in course 2 and course 3 is gradually add in some additional bits of complexity, so you can start learning how are the real CFD codes built up from these ideas of the finite volume method. And so I introduce some concepts like upwind differencing, which is something very special and unique to CFD. It's used in every CFD code. Also look at things like wall functions as well, which often people come across, and they can get a bit frightened by wall functions. So I start from very simple and just layer up the complexity bit by bit. And the way I do this is I try and use that same approach how I was originally taught back in 2010, 2012, where I actually try and build up the understanding in each stage. So rather than just giving the equations, this is how you solve it, actually explaining all of the pieces and slowly walking people through. And the way the courses are delivered, you can either get them from my website or from Udemy. They're all exactly the same. Whichever method you prefer to receive them, that's up to you. You get PDF guide which explains all of the stages, and you can use it for learning and for reference. But then also the guides are supported by working code in Excel and Python. I currently have at the moment. So whichever you prefer, you can see how from the equations where the numbers come from and how the solution is developed piece by piece. So you can actually have the working code in front of you as well, which is useful for learning. Mm-hmm. And the reason I chose to put those in Excel and Python rather than something more elaborate, maybe C or Java or Fortran or something, is most people have access to Excel and Python. And Python is also free, so you don't need to pay a MATLAB license or anything. And they're sufficiently simple that you can see the code and the equations in front of you. And chances are you don't need to worry about learning a new programming language. And you also don't need to jump into a CFD code or a manual either. They're really good. And the feedback on them has been fantastic. People have really, really appreciated them.
Yeah. I think people who have not taken a look at your course, I think they should get the material. I know the topics that you discussed in your courses, but I still got, I think, 1 and 3, just to also, if it's just support for Aidan, and because you have done a great work also with the Python code and having this nice script that you provide, like it looks very beautiful, and I think people should definitely get it if they want to learn more about CFD, the code behind it, and how to put it into a program. So I really much appreciate what you do, Aidan, and I'll put the link down to your website down in the description. Is there anything coming else in the future, maybe, Aidan, in terms of courses, maybe a book? Who knows?
Yes, I have. So as you can probably hear just from the discussions we've had, I've really only touched the surface of the number of topics I'd like to cover. I have a lot planned for the future, definitely, both in terms of free videos on YouTube and also courses as well, because I realize there's a big gap between the early stage finite difference methods that you'll learn in a university course and actually the full CFD codes that are written in OpenFOAM and Fluent and Star CCM. And often it's really, really difficult to make that jump and to come from the university and then start using a CFD code, and already there's buttons all over the place. It's not clear how they work, and the manuals don't really help either. And so my overall plan over the next few years is to really try and to bridge that gap and to provide the information and courses as well. Perhaps I can give one sneak preview that one I'm working on at the moment is a course. So the next stage after we've looked at the basics of the finite volume method of learning how to solve heat conduction in a bar and in a plate with simple examples, I'm now moving on to the next stage, which is looking at how to actually solve combined flow and heat transfer problems together. I'm looking at the lid-driven cavity flow, which is, of course, the first example you learn in OpenFOAM. It's the first stage. And the reason why this particular problem is so interesting and forms the real foundation of CFD is that we have to look at what's called a pressure velocity coupling algorithm. So you may have seen these in CFD codes, things like the simple algorithm or the piezo algorithm, for example. These algorithms are really central to how a CFD code works. And they're very tricky to learn from first principles, and some of the textbooks that are produced and explain these algorithms really aren't very clear. And so my current project is to come together with the same fantastic standard of course that really take people through and explain something really thoroughly and properly, and of course also provide working code to go along with that. So my aim is that by the end of taking that course, you will really be able to see from that point, this is exactly what's going on with the CFD code. I understand the stages in the algorithm. This is how I correct for pressure. This is how I make sure that my mass conservation is conserved, and this is how the looping goes on.
Nice.
That's to come in the future as a sneak preview.
Awesome, that's cool. When it comes to starting YouTube, was also one of your main intentions to be like the teacher you learned from? Like basically you want to be the teacher that people never had, basically. If that's correct.
Essentially, that's what I'm trying to do. I'm also perhaps I'm trying to provide the missing links that I've been looking for over the last few years. So I know this is often the case where you are running a CFD code, or perhaps you're in university and you've been given a code and you have to solve a problem. And naturally, what everyone does, including myself, is the first thing you do is you go on the internet and try and find how do I solve my problem, or what at least, how do I start, or what do the buttons mean in my code? And when I first started this a few years ago, there was really barely any information at all. And so I really want to help do my part for the CFD community to provide some of the missing pieces that I think we could really do with.
Mm-hmm. Great. When it comes to your company, is your company directly linked to your YouTube channel, or do you do something different with your consultancy? I think it is, right?
Yes. For those of you who aren't aware, I do work currently. I work full time as a CFD engineer for a consultancy, and so what that involves is solving a variety of CFD and fluid mechanics related consultancy problems for various different companies and different industries. So that I do that Monday to Friday as my standard job, and I do the YouTube and teaching in my free time. That's what I try and do as my bit extra to give back to the community. And this does give me some benefit as well, is that I am really solving these CFD problems day to day. Every day I've got another problem in a different industry with a different code, with different things to try and work out. So really, I hope that I can bring this to my teaching to give that sort of frontline information. And often you'll see this come through in my videos, is that things that I've been working on or struggling with for real life projects, I think, there's got to be a video on this. Particularly my latest one on the heat transfer coefficient, for example. This is one that was causing a bit of confusion, and I thought there's got to be a good concise explanation for this, because it's not clear. And so I then spent the time, did the research, pulled everything together, and put up the video that I thought was missing, so that I can benefit from that in the future, and everyone else can as well. And so I suppose my altruistic aim of all of this is my hope is that if I can help provide these missing bits of information and these little bits from CFD codes that are missing, that it means that everywhere around the world, people who are doing engineering in a variety of contexts, rather than spending days and hours trying to work out what the error is or the problem in their situation, they can quickly move past that problem and use it to produce better results and scientific solutions for the world. So I really do hope that it's doing a lot of good worldwide, helping people to solve their problems and to improve science for the future. That's awesome. Really what I'm trying to do.
Great. I love the altruistic approach, Aidan. Yeah. Will we see Aidan in 5 to 10 years still doing CFD?
Good question. Almost definitely yes. I really enjoy CFD. I feel like I'm really at the heart of the CFD. I'm both doing the CFD, teaching the CFD. I am also doing bits of there are bits of research that I get to be involved with as well. My various research papers are all published on ResearchGate and academia and things. If you want to read them, you can always go ahead and do those. There's also more research coming in the pipeline that I will be presenting at a few conferences over the next few years. I'm also involved with the academic side as well, which I find really interesting. For me, at least, I find CFD is a great way for me to be at the forefront of an aspect of the scientific development worldwide, which I really do enjoy.
Mm-hmm. So one last question before we jump to the questions, and then the question Rampage, which I've prepared for you. So I have 10 questions that you have to optimally answer in one sentence. Sorry. So the last question for you would be: let's say someone comes to you and says, "Hey, Aidan, I want to start my CFD journey. Where should I start?" Like very briefly, where should I start?
Oh, where should I start?
You can also say your channel.
Oh, my channel, yeah. Surprisingly, the first thing I would say is if I was presented with a stranger who said, "Aidan, I want CFD, I want to try this, what should I do?" I would actually recommend, I would say, I don't want to support them specifically, but my offhand recommendation would be go and get OpenFOAM or another free open source CFD software and just try the tutorial cases. Just jump in straight away because I really like that people can go straight away, jump in and try a bit of the code, see how it all works, and get a solution out and get some contour plots. Because that's really, I think, what the contour plots and the beautiful visualizations, the streamlines and the isosurfaces. This is, I think, part of the magic, and the part of the magic of CFD is that it helps us to really visualize things that can be quite difficult to see and understand in everyday life. I mean, we can see the movement of water. Often movement of water is something that regular people you see on a day-to-day. But seeing things like how temperature moves and how you can have hot plumes and cold fluid moving around and how it all combines together, and you often have beautiful vortex structures shed off the back of wings and planes and things. It's really quite beautiful. And so my advice for someone who just wanted to just try it out, I'd say jump in and try a tutorial case. And inevitably what will then happen is it'll be like opening Pandora's box, and they'll quickly find that the CFD world is magical and there's loads of things for them to learn and understand.
Great. Awesome. So we have 3 questions that came in before we started recording this podcast. One of them was, under the opinion of Dr. Wimshurst, is there any CFD software that will gain increasing interest in the future?
Ooh, that's a good question. Any particular CFD software? I don't think I can say any particular CFD software, but I can say that all of the major CFD softwares that people are used to, while on the surface they may appear to be staying the same, there is actually a lot of growth and development happening within the CFD codes themselves. And you may notice this, that if you use a commercial bit of CFD software, maybe every year or 6 months or so, you have to download a new version of the software. And you think, well, nothing's really changed here. Maybe it looks slightly different and I still run the same simulations as always. But actually there are a lot of very interesting algorithms and solvers that are always being added into the CFD codes. New functionality and also improvements to old functionality as well. And the way this tends to work is that often within academia or in the R&D departments of these companies is that they're facing real problems, real engineering problems, and this often prompts the development of new code or improvements to old code. And once that bit of work is done and is proved to be successful, what often then happens is that bit of code then gets advertised in conferences and reports and things like that, and then that code then finds its way into the other software as well, as everyone realizes that, oh, the code over there has got functionality to do multi-phase flow, for example. We also want that as well, and then all of the CFD codes seem to be lifting up and developing the interesting functionality. Yeah.
Great. Question number 2 we got in was using different advection schemes in an LAS simulation. For example, high resolution and central differencing scheme for the same parameters of the simulation, boundary initial conditions, properties, etc. Should we expect different results?
It's a very good question. One thing I've definitely found is changing the discretization schemes, whether you're in RANS or LES, does tend to affect the solution. And this is part of the reason why you're actually given the choice of advection or convection schemes in CFD codes, is that it does tend to affect the solution. The question is, with many things in CFD, is often how much does it affect the solution, and do I care about that? And so this is particularly difficult with LES because, of course, your calculations take a long time to run. LES is very expensive to do. And you will find a similar thing in RANS. It will affect the results. But as always, what I tend to recommend doing in CFD is, because many things are very difficult and it's often not clear what's going on, you can often treat a CFD problem as a black box. You can treat your CFD code as some kind of unknown. And what you can do is try the different schemes, try them out. And then, as we were talking about before, actually look at the result that you're interested in and see what effect does it have on that particular thing. So if we went back to the aerofoil example, for example, there are many things you could look at on the aerofoil if you were running an LES or a RAN simulation of flow over an aerofoil. If you were only interested in the mean lift coefficient, for example, you could run your different advection schemes and then have a look, how much does this affect the mean lift coefficient, because that's what I'm interested in. If the effect is very small, do I care about that? Does it affect it? Can I just account for that by putting an uncertainty on my solution? Can I say the lift coefficient is 1.27 plus or minus 0.1%? Would that be okay? And also this does, I know this can appear like a bit of a difficulty. I don't know what scheme to use, but this is the kind of thing that if you're doing an academic study, or even an industrial study, can help improve the confidence in your results. If you then say, we realize that there's an uncertainty in the advection scheme, we've looked at the different schemes, and here are the differences. And we find that the difference is this percent. And so then the question then becomes, how do I know which one is correct? I may have one that gives me a lift coefficient of 1.27, 1.28, and 1.29. Which one is correct? The one in the middle is not necessarily correct. How do I know? So usually a thing you can do here is you can take a small test problem. So something very simple, which usually everyone will be aware of. Something like for LES, you could look at flow in a rectangular channel, or the backward facing step flow. Something very simple and easy where you have experimental data available. That's the key bit. And then you've got a very simple case. It's very small. You can set up your LES, your RANs, very quick to run, and actually look at what are the effects of the different parameters. And the key distinction you can make here is you could have your value of 1.27, 1.28, 1.29, and you can look at your other parameters, and you can say, for this experiment, this scheme gives me the closest agreement with the experiments. Therefore, I believe this is the correct scheme to use. And you then have to make the argument that, for example, you would say the flow in this test case is sufficiently similar to my real case that I can deduce that the advection scheme that was correct here is most likely to also be correct over here. So you do have to do a bit of justification, but you can get there if you think carefully about it.
Great explanation. Thanks, Aidan. The last one is a bit longer, so I'll try to read slowly. According to Dr. Wimshurst's lectures, each cell of the mesh for LES simulations should have a certain cell size in order to resolve at least the 80% of the total kinetic energy. This information can be calculated by various post-processing software. Is Dr. Wimshurst aware if any mesh generation software could take as input this cell size information and generate automatic the mesh? If not, is there any potential for such an operation? I believe that it would be more than interesting. That's a question.
Yeah. I see I know the example we've been given here in the question is about LES, but it's actually a bit more of a broader question if you think about it, where what we're saying is there a way that given a solution, I can go back to the mesh and refine it to improve the resolution of those flow features? And this may not be a direct answer to your question with LES, but this kind of technology people have definitely looked at before. It's often called adaptive mesh refinement, is something people have looked at, where on the fly, what the CFD code will do is look locally at the solution and refine the solution locally around flow features, typically free surfaces and shocks and things like that. So that kind of adaptive mesh refinement is available on the fly to look at things in general, where you want to refine meshes locally. But in terms of LES, it tends to be quite difficult to do because I don't know if there is any capability at the moment. I certainly haven't done it myself. And I know there is that big manual step of having to go in to your solution, look at the turbulent kinetic energy field and see what percentage am I resolving. Can I then go back into the mesh and do that? There's not something I know of at the moment, but there's definitely potential for it to be developed. As always with the development of new technologies and things, it's worth bearing in mind that the majority of CFD solutions are still carried out with RANs. The majority of industrial cases do use RANs, and LES does tend to be used mostly by academics and academic studies. And so the drive is still on improving RANs, and this is why you tend to see most of the improvements, like the adaptive mesh refinement, focused on RANs. But I imagine over the next few years, as we see continuing improvements in computers themselves and the solution algorithms, that LES may become more feasible. And then you can imagine a world maybe in a few years' time when LES is more commonplace and people are saying, this is a problem which keeps coming up every time we make our mesh, and we have to assess the turbulent kinetic energy and the time step and then go back in and make another mesh, and it's really inefficient. And will then become the driver for developing a new algorithm or a technology.
Mm-hmm. Thank you so much, Aidan. So with that being said, let's wrap things up and jump to the question Rampage. There are some questions that you might have... Yeah, there might be some questions you might have heard of in other podcasts, but that's the point of the question Rampage, to see what different people say to the same question. Question number 1 is, Aidan, what are you most proud of?
Oh, what am I most proud of? I suppose I'll give two answers to that. The first answer being what my technically most proud of would probably be when, as part of my PhD, one of the problems I was trying to solve at the time was a very tricky one around tip correction factors for wind turbines. And to understand what a tip correction factor is and why you need it for a wind turbine, if you think of an aeroplane, aeroplanes often have a winglet at the end where the wing is bent up, and that's essentially to do with the tip vortex that's shed from the back of an aeroplane wing and affecting the aerodynamics. You get a similar effect on a wind turbine blade or a tidal turbine blade, where you will also have a tip vortex that's shed from the blade as it's rotating. And that's perhaps the difficult bit, is that you have a tip vortex that's rotating with the turbine, and that will of course also depend on how fast the wind turbine is rotating. That will change all of the aerodynamics. And if you read my thesis, if you want to read my thesis, all the information is in there if you're interested. But within the wind energy community and the tidal energy community, there has long been a lot of confusion around how you account for that tip vortex rotating with the turbine blade in various codes and various aerodynamic codes, how you account for that, what sort of correction factor do you use? Not only was there a lot of confusion, but there was also not a clear way forward. People didn't really know how to address it. And I spent a long time in my PhD looking at the problem and trying to work it out. It was really very challenging. And in the end, I did actually manage to work out what was going on with the differences, where people were getting confused. And I think that's probably the most useful aspect, is that I worked out where people were getting confused, why, and then actually put together a comprehensive framework to address it. It was fantastic. I was really, really proud of it. And it got published in several papers in wind energy, which you could also read if you were interested in. So that perhaps would be my technical thing that I'm most proud of in my life. But my second one would perhaps be more of a social thing. And my social thing that I'm most proud of perhaps is just generally seeing many of my family and friends who I spend a lot of time with, seeing them having a fantastic time in life, enjoying themselves, succeeding, me helping them, and just being there along the journey, and just being a part of a lovely community of people who are having a fantastic time, enjoying themselves, improving the world and trying to make the world a better place. And it makes me really proud that I can be a part of, even as a friend or a family member, just to other people who are also having a fantastic life. It's really amazing.
Great, excellent answer, I love it. Question number 2, what was your biggest failure and what did you learn from it?
My biggest failure. My biggest failure. So perhaps I'll go with the technical. I'll go with the technical answer first, and then I'll give a social answer as well. My technical answer would be, I will say it's a failure, but it's also, as most failures are, they're also a very good learning experience. When I first started my PhD, I was looking at a problem with tidal turbines and trying to work out what would happen with a collection of tidal turbines that were installed on a slope on the seabed. And the reason why this is an interesting problem is often you assume, if you're doing a wind energy simulation or a tidal energy simulation, if you've ever done the CFD, you put a big box, you have a big box with an inlet and an outlet, and then you have your spinning turbine in the middle. And most of these simulations assume that the ground is flat. And that's what you do for most simulations. You're probably aware, for external flow simulations, you have a square box with your object in the middle. And with tidal turbines, what's quite interesting is that the sea that the tidal turbines are installed with is often not very deep. It's maybe 30 or 40 meters deep. And so that you have the free surface is actually quite close to the floor. What that means for your CFD simulation is that you have your box as normal with your turbine in the middle, but the top surface is actually very close to the bottom surface. And you have what's almost like a channel flow. You have a channel flow or a pipe flow with your rotating turbine in the middle. And the question I was looking at is, what happens if the floor isn't flat? What happens if it's at a surface, if it's at an angle? Is that going to affect the flow as it goes through the turbine? Maybe it's going to accelerate or expand. What's going to happen to the vortex pattern? And as that comes off the back, is that going to affect the performance of the turbine? And originally, when I started my PhD process, I thought that perhaps I could solve this problem by hand using some very simple hand calculation models with things like Bernoulli's equation, which I'm sure people know of. And I spent about 4 months looking at this problem and using different methods to try and solve it by hand. And in the end, after about 4 months, I found that you could not solve it by hand. I managed to get to a point where I realized, you just can't solve it by hand. And so in terms of a technical failure, I had wasted 4 or 5 months of a PhD process doing this, going down a dead end. And I'm sure many people who've done masters or PhDs will have similar experiences where you try running experiments or looking at things in science, and you find that unfortunately this science does not work. The science doesn't work. I want it to work. I really want it to work, but the science doesn't work and we can't pursue this. And there are numerous examples of this throughout history as well, of people who've investigated crazy ideas or inventions and it just hasn't worked. And so it was a failure in that sense, that I wasted a lot of time and it was very stressful. But for me, it was it was a fantastic learning experience to be really at the heart of science, where you realize that in new science, not everything works out. You can't force new science. The new discoveries don't just appear. Often most discoveries are incorrect, and you find out they can't work. And it's very disheartening as well if you are a PhD or a master's student to go down a dead end, because of course you can't ultimately present a theory that's not correct. You have to come up with something new in science. So that would be my technical failure. I suppose in my social failure would be something more general that I'm sure other people have found this as well. Is definitely looking back at the past few years, I think my social failure would be not spending enough time with family and friends. I think that's definitely a social failure, which comes often with very difficult work. Science, technology, engineering, and software development and things. It takes a lot of time to write the code, to run the experiments, time in the lab or on the supercomputer. And one thing I found is, of course, you can work late into the night and put lots of hours into developing your new code, but that often comes as a result of not spending enough time with family and friends and people who you like spending time with. So I'd say that's definitely my social failure, and my recommendation to everyone would be try and look at the balance in your life and try and get the balance between your science and your family and friends. And perhaps having the coronavirus around the world has maybe brought that into greater focus as well, that often we can be separated from family and friends for a while.
Love it. Question number 3. What advice would you give someone wanting to be as good in CFD as you are?
Oh, somebody wanting to be as good at CFD as I am. First thing I would say is I'm definitely not the best at CFD. I'm still learning. I think everyone is learning. My advice, I can tell people to how they could try and become similar to me if they wanted. What I found has worked for me would be taking the time to do things slowly. I think that would be my best bit of advice, is that it's very tantalizing and very inviting when you're given your CFD problem, or you identify your CFD problem, to rush straight for the solution. And that's fine. If that's what you need to do for your deliverable or your report or your thesis, for example, to rush straight for the solution to get the numbers out. But often that means missing the understanding that comes along the way. And some of the greater understanding, at least in CFD, comes from when you spend 3 months making a mesh, which I had to do. I spent 3 months making one mesh, and that can be infuriating. You spend months and months doing something, and you have to try and understand what does this button do? This bit of functionality ruins my mesh. It never works. This is really the golden thing that works. And actually slowing down and spending a lot more time in the stages of the process, reading the manual, looking up on the forums what other people have done, speaking to your friends, can help you develop a depth of understanding rather than a breadth of understanding. So running a lot of CFD problems would give you a breadth of understanding, but I personally have found I tend to prefer the depth of understanding, and so taking things slower has worked for me. That's what I would say.
Excellent. If you could spend one day with a celebrity, who would it be?
Oh, one day with a celebrity. I suppose the very easy question to that would be, I'm going to say Elon Musk, but not for the reason that people would expect. I'd like to spend a day with Elon Musk because I'm interested in how they've done CFD for their hypersonic vehicles for SpaceX. That's what I'd like to know. I would like to know what really goes on behind the scenes.
Yeah.
How have they set up the calculations to run when the Mach number really? What have they done, and what's really going on behind the scenes? So perhaps it's not him exactly that I'd like to speak to, but I would be really interested in speaking to someone from the technical team that he leads, perhaps.
Interesting. Yeah.
So it's the high speed CFD and the hypersonic CFD is very challenging to do, and love to pick their brains and to find out what's going on behind the scenes for the simulations. Yeah,
love it. Cool answer. Question number 5: a video that you enjoyed recording the most on your channel.
The most recorded video. You have to give me a second to think about that one.
What did you enjoy recording the most? Was it maybe Y+, wall functions, anything else?
I think I would probably have to say the videos I enjoy doing the most are definitely this is probably the case for everyone as well, is that I try with my video uploads at least to produce a mix of videos, and to have some videos which are more foundational and which are more essential for understanding. And then I also try and produce some videos which are more complicated and require a bit more deeper knowledge. And often with some of the more complicated videos, I've taken all of the source material and have spent a long time actually thinking about it, because often there are missing links. And I think that's the bit that I do try and bring out with the videos, is that often you've got the paper and you've got the manual and you've got the code and you're trying to work out what's going on, and there's that missing link that isn't really written down, that nobody has explained. Actually, the thing that you need to understand is this is what makes it all work. This is the secret sauce, as they often call it in some industries. This is the secret sauce. This is the key to understand, to really get this. And there were definitely 1 or 2 videos where I've had that, particularly even my first video on wall functions, the original video which I first recorded, when I had the spark of inspiration where I realized all of a sudden that's the key. That's what people need to understand. That's what makes all of the pieces of the puzzle fit together. And so I think I would say my first video, actually, because I had a very simple moment of understanding, which has helped make all of the wall functions and the wall treatment and the boundary layers and everything has fallen into place. And for those of you who haven't seen the video, it's quite an old video, so the production quality is not great. But the key idea in that, and if I could say this to everyone in the CFD community, this would be the one takeaway message that I would give to everyone in the CFD community, is to remember that in a finite volume method with a cell in a mesh, you've got your mesh cell. It's important to remember that the flow variables, so velocity, pressure, temperature, can only vary linearly across the cell. The best you can get is linear across the cell. And the reason why that's important, and this is the key bit of understanding, is that in the cell that's next to the wall, so you have your wall in your CFD code and you've got the cell that's sitting on top of the wall. If you make a Google search and you look for law of the wall, logarithmic profile, logarithmic law of the wall, and you skip past my video and click on one of the other links, what you'll see is the classic shaped profile, which goes up. It's u plus is equal to y plus, and then you've got the logarithmic region. And the key bit of understanding here is that it's very easy to look at that and think what the CFD code is doing is putting a logarithmic profile between the wall and the cell centroid. That profile is just being fit into that bit of the cell, and that is not true. That's the key misunderstanding, and the bit that I finally realized for that video, and it's why I'm so proud of it, is that the flow profile can only vary linearly in the CFD code. It's linear between the wall and the cell centroid. So it's 0 at the wall and it has a value at the cell centroid. And that is where all of the wall function methodology slots into place, is because you realize the profile should be logarithmic, but it can only be linear. The best you can do is linear. And so what the wall functions do is they're actually a correction to that to account for the profile being wrong, but it's not changing the profile itself. And I think when I had that bit of realization, I was really happy, and I thought I finally cracked it, and I've got to share this with the CFD world, which is why it was my first video. And I'm sure that anyone listening who works as a CFD engineer who does CFD on a regular basis will often come across people with the misconception, you may have it yourself, where you think, I'm using a logarithmic profile for my wall function, so there's a log profile between the wall and the cell centroid. It's not true. That's not there. It's linear, and there are corrections to usually the wall shear stress or the flux to correct for that profile being wrong.
Yeah, excellent. Mind-blowing. Thanks a lot, Aidan.
A very small mind blow, but it was mine. So,
but still, I think it's very important to mention this. Next question is 3 most influential people in your life.
Oh, 3 most influential people in my life. The first person I'm going to say, I'm just going to use as an agglomerate. I'm going to say my family. I'm going to say my close family. So my parents and my brothers. I'm going to agglomerate them as one person because I think that's fair. So my family have been definitely the biggest influence on my life. They're fantastic. They're incredibly loving and supporting family, and I'm so grateful for having them and all of the support they continue to give me. They're going to be number 1. The second probably is going to be that first teacher that I had back in. I don't want to name anyone. I don't want to name because we're on the internet. I don't want to name anyone. But my first teacher back when I was learning what fluid mechanics was, because for me that was they were the person that finally provided me with a framework to fit all of the models together for how a fluid really behaves, and by extension from that I could then see how you could also treat solids and other continua and materials, and that was like a kind of a eureka moment as well, how everything started to fit together. And I suppose the third person I would use, I'm probably also going to give a bit of a boring response and say the agglomeration of friends I've had over my lifetime as well, is I found that I've learned a fantastic amount from my friends through every stage of my life. In university, when I'm learning the fundamentals of engineering and science, and then through my PhD, my working life, and also friends who you perhaps have in a social context as well. I think friends are so fantastic as well, because friends always have a completely different experience in life to what you do, and they provide that lovely external influence of new ideas, and they present you with new things which you may have thought of before. They provide friendship, laughter, and I think I'm incredibly grateful to each and every one of my friends for providing that. They've been absolutely fantastic. Not that 1, 2, and 3 are in order. I should also say that as well.
That's
I'm gonna prioritize all of my friends after my lecturer. 1, 2, and 3 are not in order.
Yeah. Excellent. Very short question number 7. Favorite movie?
Oh, my favorite movie. I have lots of favorite movies.
Saying post-processing videos is not
post-processing videos. Yeah. Perhaps I'll choose I'm only gonna pick one. I'll pick quite an unusual movie. I'm gonna pick a movie called 12 Angry Men. I don't know if you've seen 12 Angry Men.
No.
So this would be my movie of choice. It's a very old film. It's very old. It's in black and white if you watch it, and like most people, I'm often very skeptical of old films, but 12 Angry Men is a fantastic film, which is set in the jury room of a courthouse, where they have a murder case, and the entire movie is set in one scene in the jury room. And the reason it's called 12 Angry Men is there are 12 members of the jury around the table, and the entire film I think it's shot in only a few takes, and it's one set in one room, and you think, God, there can't be a lot that can happen in one set in one room, and it's old and it's black and white, but it's an absolutely fantastic story. It has amazing twists and turns, and you get to see the change in different characters, and when new incidents are injected into the set, it's really fantastic. And every single person I know who's watched it has said it's absolutely fantastic film. So I'd recommend 12 Angry Men, I think would be my film to recommend.
Good recommendation, thanks. Question number 8. If you would be in my shoes, what would you have asked yourself that I did not?
Ooh. What would I... I think you did ask the question, which was, what's my... what do I think is going to happen in the future? probably I would ask, which is always one of the hardest questions to ask people, because we can never really predict the future. The future is a bit of a chaotic system, and so we can always just take a guess, kind of like a CFD code. You just take a small guess at what you think is going to happen in the future. That's probably what I would have asked. Mm-hmm. And my answer to that would be, what do I think is going to happen in the future? Generally, for the CFD community as well, as I think that actually, even though we are seeing the emergence of many fantastic new technologies these days, I do think that CFD will still hold a critical role in the future, and I actually believe it will grow over the next few years. I think CFD will even though it's an old traditional technology, will continue to grow and improve over the next few years. And the reason I see that is just around the world in current events, we often hear about the importance of and that governments are moving towards greener energy systems, for example. Various governments and committees around the world are looking at how can we develop cleaner energy systems, and how can we be more efficient in general. I think that's often what they're getting at, is how can we be more efficient in general. And you can be, if you're in a transport vehicle, you can be more efficient by streamlining and improving the aerodynamics of your system. If you're an energy generator, if you have some kind of power station, be it coal, natural gas, nuclear, you want to know, how can I extract my energy more efficiently and use it, and perhaps capture some greenhouse gases or emissions. And so what I see is that there is a heavy niche for CFD in many of the burning questions that are faced by governments and industries around the world. And so I think that there's a bright future for CFD, definitely.
Great. Question number 9. One superpower you would like to have?
Oh, one superpower. I've thought about this a few times. And I think that a very interesting superpower might be to have perfect accuracy. I think would be a very interesting superpower to have. So if you just think about everyday activities that you have, if you were trying to throw a ball, for example, and catch something, you would always have perfect accuracy and never miss, never drop anything. You'd always be able to catch things. I think that could be a very interesting and unusual superpower, particularly if you were in sports. I think it could be very useful. You'd also be fantastic at typing as well. You'd quickly become the world's fastest typer, because you'd never miss a key ever. You'd never have to spend hours hitting the backspace key to delete things. I think having perfect accuracy would be a very interesting superpower. That's what I'd like to see.
Yeah. Just imagine building a block mesh with accuracy.
You'd never have to untwist your blocks in block mesh either.
That's right.
Although, would you get a perfect mesh every time? I suppose you'd get the best possible mesh that you could do every time.
Probably, yeah. Probably. So accuracy is a good answer. That's good.
Yeah.
Question number 10. If you were a superhero, what would your name be?
Oh, what would my name be? I suppose Accuracy Man would be very boring. If
I thought about it for a second.
Accuracy. Yeah, Accuracy Man. That's not really going to work, is it? Accuracy Man.
maybe Acumen. So it like
Acumen.
It's like a wordplay with Acumen.
Acumen, yeah, and I like Acumen, yeah, definitely better than Never Miss Man or Perfect Accuracy Man.
Too long.
or Boring and Plain Superpower Man. You could also have that as well.
Yeah, that's right.
Rather than super strength or flying or telling the future.
Yeah. So these are the 10 questions. I thought about maybe an extra question, because when I asked the question, if you would be in my shoes, what would you have asked yourself? Then you had kind of this analogy how life is chaotic and you have always these changes in initial conditions. If you would be a CFD code, what CFD code would you be?
Oh, if you were a CFD code, what CFD code would you be? I think I would probably be OpenFOAM 2.3. That's what I would be if I was a CFD code. An early stage TFD code that you could understand reasonably well and did an okay job, but definitely had a bright future ahead and looking forward to improvements in the future. I think OpenFOAM 2.3 will always have a special place in my heart. Awesome. Especially some of the bugs.
I like the philosophical answer, Aidan.
Yeah.
Cool. Very nice, very long podcast. Actually, we talked about a lot of stuff. You talked about a lot of stuff, and I think people have now an understanding who is Aidan, what do you actually do, and we talked about your course and a lot of other stuff. Is there anything else as a closing remark from your side, Aidan, before we wrap things up?
Oh no, I think the podcast has been fantastic. I've really enjoyed it. I've really enjoyed coming on your show. It's been fantastic to finally be a part of it and join the library of other fantastic and interesting individuals you have on your podcast as well. And you've been a fantastic interviewer as well. You've asked some really good questions. I really appreciate it. Thank you.
Thank you so much. Very flattering. And with that being said, thank you so much, Aidan, for participating, and hope there might be a second part in the future. Who knows? You're always invited. You're always invited. For example, if a course comes out, what we can also think about is maybe that you do something live, maybe on your channel, maybe on my channel, and just code a system, and people could join and ask you questions. That would also be a nice idea to have in the future. But yeah, with that being said, thank you so much, and I wish you an awesome weekend, rest of the weekend, and see you on social media, I guess, then.
Fantastic. Thank you very much, Joseph.
Yeah.